All right. So, Ariel approached me a few weeks ago asking me if I'd be willing to give a talk on this paper that Pablo Fonfria, who is the first author, is a postdoc over in Spain and a collaborator since I joined the XYZ team in 2016, wrote on some data from my program, which I'll highlight later. And I was happy to give a talk and present Pablo's work that has been brilliant with this XYZ data that has come out of this program. Our other collaborators are listed below as authors on the paper, and then I provided the where you can find it in ANA or archive, depending on how you get your access to the journals. And then before also going more into the paper, I guess as an XYZ instrument team member, I like to highlight all of the excellent work and data that we have in our archive, and as part of the synergy effort with the infrared archive and IRTF in particular, highlight some of the work that's been done with some of the other IRTF instruments, namely both iShell and TEXES, TEXES being the sister instrument and forerunner of XYZ. And it's all, as of right now, sort of been in this gear towards high mass protostars, hot cores, star formation area. Um, the papers are there, relevant Sophia proposal, since it's also part of the SARP call. If you're searching the archive, those are the proposals you want to search for to find the data, some of which is public, some of which is still proprietary, especially in the cycle 9 part. And then links to the Sophia archive, the IRTF archive, which currently only has iShell and specs, but Nassim Rangwala has been leading an effort to get the TEXES archive as part of this. But otherwise, if you do want TEXES data, you have to contact the TEXES instrument team, Tommy Greathouse, Rahini Giles, and they'll work with you to try to get the data that you need. I also want to preface before also going into the talk that when we discuss XYZ and TEXES units, we use this sort of historic unit of wave numbers in inverse centimeters. And just as a reference, wave numbers is to take 10,000 divided by the wavelength in microns, and basically then you'll know where we are. So like 1,000 wave numbers is just 10 microns. And then talking about spectral resolution, it's basically R is the wavelength over the dispersion in the wavelength, and highlighting some Matt Richter's, the PI of XYZ, his review talk on high resolution IR spectroscopy at IR 2022, and two references about the XYZ instrument that you can either find on the Sophia webpage or in the literature, the XYZ instrument paper. So jumping now into sort of the science and some introductory information about this talk. As we know, stars have a life cycle. They go from protostar to being on the main sequence. On the left there, you have an HR diagram showing the main sequence and isochrones at various points showing how the stars evolve over time. And on the right is an artist representation of this process where we go from a main sequence sun over here on the left. And let me know if my cursor doesn't appear, but I'm gesturing sort of on the left side of the image there. And as it steadily evolves off of the main sequence, it starts to become larger, becoming first a red giant, then a asymptotic giant branch star, before ending over here and as represented by a planetary nebula. And Y-Canvan is sort of in this step right before here, one of these two stages on the asymptotic giant branch star, which I think a representation like this sort of omits that before you get to this layer, you are constantly shedding and having mass loss during these stages that sort of built up these envelopes. On the left here, you can see actual data from ALMA of the AGB star R Sculptoris, showing this incredible morphology as you go through the different velocity bins. And then on the right here is a schematic of what the circumstellar envelope or environments, both CSE, look like for these stars. On the top of the diagram, sort of splitting it in the oxygen rich, on the bottom by carbon rich. And where we sort of study in the mid-infrared with spectroscopy is this molecular formation zone, a few tens to hundreds of stellar radii away from the central source. And just explaining the difference of oxygen to carbon-rich stars. Basically, it's the carbon to oxygen ratio in the circumstellar envelope. If oxygen dominates, it's an O-rich or M-type. M-type to me is a little bit disservice since we also use M as a spectral class, so it can get confusing when you're talking about M-type stars. S-type stars are where the C to O ratio is basically around unity, and carbon AGB stars are when the carbon starts to dominate the envelope, usually after what's called the third dredge up. And at the bottom here is a paper from Miguel Agundez in 2020, where he plots how various molecules should expect their abundances from about 1 stellar radii away from the photosphere out to 10. And you can sort of see how the different chemistries dominate in different types. And so that led Pablo and I in 2017 in Sophia Cycle 6 to put a proposal in where we wanted to look how mass loss rates impact the chemical abundances of these circumstellar envelopes. It was selected as priority 1. We put in 3 types of oxygen-rich stars at the 3 different bins, a sort of low mass loss rate, an intermediate mass loss rate, and a high mass loss rate. So 3 each for oxygen and carbon type, 2 for S type because they don't seem to have as high a mass loss rate as the stars that are fully in one or the other 2 camps. And then YCAN Van, highlighted there in bold since that's the subject of our talk, was our low mass carbon type AGB star. And so focusing more on YCAN Van, as shown there in an astronomy picture of the day image on the left. It's what's known as a J-type carbon-rich star. So then within the classification of it being a carbon-rich envelope, it just happens to be enriched in carbon-13 for reasons that aren't fully understood yet as to why some of these stars are different. Its ratio is about 3 there, and as a reference, normal quote-unquote carbon stars usually have that ratio anywhere from 30 to 100. Some other facts there that were also parameters for our modeling that will be presented later are also given, as well as the velocity of the star in LSR and, excuse me, the expansion envelope of the envelope, expansion velocity of the envelope. And so jumping into the data, which also correspond to the first 2 figures, these are a preliminary version of this figure that Pablo put together, showing just how rich this envelope turned out to be. At the top of both of these are all the HCN lines, which are the focus of the paper. But underneath, you can see that on the left here, he plots acetylene and one of the isotopes of acetylene with carbon-13 swapped in. And on the right is with the molecule CS and 2 of its isotopologues, carbon-13 CS and C34S. And this just turned out to be a really, really dense spectra. Like as soon as we took the data and did a quick look of it, you could tell that the star was really, really interesting. What I have boxed are to show that these are the data taken with hexes, and on the right in our sort of high-low mode where we use a short slit to cover anywhere from 20 to 40 wave numbers at a time. And on the left here is at the top is the Texas data centered near 13.9 microns, and X's data, and at the bottom here is the Texas data around 13.6 microns, where the transmission from the ground is a little bit easier to do these studies. So once we take away sort of making these plots as busy as they can be, even though they're still very busy, you can see that HCN is just all over the place. Strong P Cygni profiles at the 13 to 14 micron range, and just pure absorption in the 7.5 central wavelength range for these settings. And HCN is a great molecule to study because it's a parent molecule. It's one of the first molecules that should form in the circumstellar envelope. And so that allows you to actually trace anywhere from a few stellar radii out to where it should disassociate at around 180 stellar radii in YCAN Van. And what I won't be showing is the IRM 30 meter data that we also have. I have a bonus slide on what those data look like. But one of the first tasks that we did after putting this together is Pablo worked on fitting the continuum, which required going to the ISO archive and taking the SWS and LWS, the short wavelength and long wavelength spectrograph data. So building an SCD from about 1 to 100 microns, and found that it was fit best with three components: a sort of black body to represent the central source of YCAN-VAN. What he found when doing this was that the inner region is dominated by amorphous silicate carbide, and the outer region by just generic amorphous carbon or graphite, which was a bit of a surprise because if you compare this to IRC 10216, what's seen as the sort of archetypical carbon star, amorphous carbon actually plays a larger role in those inner few radii close to the stars. So already, when you're just looking at the continuum, you can see that there's a difference of the dust properties through the circumstellar envelope. And then in that inset there, we just highlighted some other molecular contributions to the ISO SWS that we're still seeing, sort of with that resolution of about 2000, compared to our resolution of 60 to 72,000 with our XEs and TEXEs data. And so one of the first order things that you can do once you also have a continuum and it's been fit so that you can now calculate what's called a row vibrational diagram. And it's a sort of proxy of comparing the column density to the rotational energy. In this case, when we're dealing with the absorption components, you do it compared to the lower state energy rotation. If we were going to do for the emission part of the P Cygnis, we would look at it in terms of the upper state. And plotted here are for both the 7.5 and 13 to 14 micron data with the offset so that it all fits on one plot. And what becomes apparent right away is there's sort of four different components to the HCN that Pablo called cold, warm, hot, and very hot. The hot data was a little bit lower in signal to noise, so that's why you can see that the error bars can be pretty large, nearly a factor of 2. And the other thing that came out of this was one of the components that when you try to fit it shows this sort of positive trend, which you usually don't see. It's a bit of an unphysical, implying a negative rotation energy temperature, or rotation temperature. And when you pull this out and you get an idea of the column density from this, these values here were already about 0.02 to 0.32 times that of what's in IRC 10216, which sounds like it should make sense, but it is a lot, implies also that the HCN column density is a lot higher than you would expect in a low mass rate envelope when IRC 10216's mass loss rate is about 200 times higher than that of YCAN-VANs. So then as we started to actually Pablo started to fit the lines to the envelope. What he found first was in red in these figures is the fit to the data with just using that data. So plotted here would be the 7.5 micron lines, a sample of them. And the red is only fitting that. The blue line above that is trying to fit the line using the data from the other mid-infrared, so the 13 to 14 micron XEs and TEXEs data. And then the green line was when Pablo decided to found that he wasn't able to fit with a spherically symmetric envelope, something that agreed between both channels. And so he took his model and made it a 2D asymmetric envelope and found better agreement by doing that. So this is the 7.5 micron lines showing that when you fit it the other way of the 7.5 micron, the blue lines don't really align with what just using the 13 and 14 lines in red would do. While then with the asymmetric envelope in green again, you get a much better match to what the features are doing. These arrows here on the left in the QE branch point to what we call that as a possible evidence for an additional redshifted component that was in the wings of these lines. It was also something seen in the IRM millimeter data, which I have a slide on as a bonus slide later that would point out something similar that was seen in that. And so as we were modeling and also doing this envelope, what we found that was also why we couldn't fit as a good, simple, symmetric, spherically expanding envelope is that the lines were always a bit wider or sometimes moving at a little bit faster velocity than what we would have expected. And so we tried different cases of changing either the turbulent velocity or different velocity for the different changes to the gas expansion velocity. So this figure in the paper sort of highlights comparing to, again, red is the best fit model, and then blue was having the gas expansion velocity set to 8 kilometers per second, while green was when the turbulent velocity was set to 5. And the red best fit was when the gas expansion velocity could go and range from anywhere from about 0.5 to 8 and up to a little bit faster, even 10 kilometers a second. And that we found actually that when the turbulent velocity was 6 kilometers a second, so a lot more turbulent than you would expect in a thin, optically thin, sort of what you would think controlled low mass loss rate envelope, the lines had a better fit, suggesting, like I said, that there's more either there's mass ejection happening or just a lot more turbulence in the inner envelope. And so what that looks like as sort of plotted and making a 2D image of what the model would look like. On the left is the zoomed out showing the whole envelope that was looked at from about 0 to 400 stellar radii. The dashed line, the first one at around 170 stellar radii, is the HCN photo disassociation region. Anything outside of that, HCN should be disassociated by UV photons from the interstellar radiation field. And at about 380, that outer yellow line is where you would get self-absorption for the millimeter data of HCN. And so just the panels from top to bottom are the H2 density, the abundance of HCN compared to H2, the rotational temperature for the ground state line, and the line of sight velocity where this direction Earth is over here. And so the envelope is expanding towards us in this direction, expanding outwards over here. And then on the right is a zoomed in version to a few tens of stellar radii. And down here, you can sort of see where in the abundance, there's a bit of a asymmetry where it's not a constant density throughout like it is more out here in this outer envelope. And we sort of either chalk this up to sort of like a line of just how we're viewing it from Earth, that maybe there's some implied like just geometry of like a view to how the material is expanding outward to us in this model. So it's a quick highlight of a summary for a few other slides. Our high spectral resolution mid-infrared observations found that the Wide-Can Van circumstellar envelope was very chemically rich. We identified 130 lines of HCN and its isotopolog H13CN. I have a slide on the H13CN later if anyone has questions about it. We found our measurement of the carbon 12 to carbon 13 was about 2.5, which agrees with other values in the literature, which range from about 2 to 8. We also identified acetylene and a lot of our carbonosulfide in the envelope that we didn't do anything with other than sort of pointing out that it was there. And we complemented that data with the IRM 30 meter observations. We found some interesting evidence about the sort of dust contribution at various points in the circumstellar envelope. And I want to highlight down here at the bottom that one of the things that is also part of this being an asymmetric envelope, we found that the rotational and vibrational temperature of HCN is just out of LTE, local thermodynamic equilibrium, throughout the whole envelope. And sort of as in the spirit of this also being connected to the Sophia archival review proposal, I want to highlight some data that should be going into the archive in the next few weeks. Is from a cycle 10 proposal that I submitted. It might have a new name as a director's discretionary proposal. That's sort of something in the background, but if you're searching it, either it'll be this 100149 identifier, or it might have a new 75 and some stem after that. And all of this data is going to be public. What we had intended to deliver was our 50,000 or in velocity space 6 kilometers per second resolution high-low observations of a bunch of targets from the solar system to pre-main sequence stars to a bunch of different type of post-main sequence objects. And so we were able to get 3 sources in the most recent Axes campaign. 2 of the 2 pre-main sequence, our hot core targets, have new data, and we were able to actually complete at higher than intended, just because IRC 10216 as the one of the brightest mid-infrared sources in the sky was very forgiving. We actually used a narrower slit to get higher resolution, and we completed the whole 5.3 to 28.3 micron range. And so that data will be available to everyone. And just to note that once you go out of past 19 microns with XCs, there are just natural gaps in the data from the orders being larger than what the detector can fit. I wanted to highlight the people who helped me put this proposal together. It was a great large team and covered everything, again, from solar system and exoplanet enthusiasts to people focusing on evolved stars. And I'll leave up my summary for any questions again.
All right, thanks, Ed. Any questions from the audience? Feel free to unmute yourself.
Yeah, this is Kyle. I have a question about the row vibrational temperatures being out of equilibrium. Is it, having not really looked at too many HCN excitation diagrams myself, are they typically in thermal equilibrium, or is this kind of a common thing that you see in objects like this?
That's a great question. I guess that for me, this is the only one that I've seen. And so for for me, it's a one of one case, and all of them being not in equilibrium. I don't know for other stars. I would imagine in 10216 maybe is in equilibrium, but I haven't seen HCN vibration diagrams for other carbon stars yet myself.
And what is I mean, obviously it's not an equilibrium, but is it mostly chemical excitation that seems to be causing the out of equilibrium?
Yeah, and so I think part of that is to why we couldn't fit, right, a single symmetric expanding envelope. So the asymmetries that Pablo introduced, sort of, this where it looks like, as we're viewing it, there's this sort of region right in front of us that we happen to be viewing that appears different than what's around it, and even behind it, you're seeing a little bit different in the abundance. That these stars, especially at the low mass loss rate, because they're not as bright in the mid-infrared, have historically been understudied. And a lot of this was just sort of new that we've done, that we're sort of, the paper, our language in the paper is very much of like, hey, this is something we found. It'd be great if more of these stars were studied in the future.
Yeah, it certainly sounds like there's a lot of like future work that could be done with these excitation diagrams.
Yeah, and I guess it'll sort of shift more to the ground, where taxis or Vizier in the south, but basically, and then you could still do data. So showing sort of what the IRM 30 meter data even look like, you can sort of see that we point out again this red wing, and some of these effects like up at the top are from these lines also being maser lines. So there's also just additional pumping that's happening that is this envelope. It just appears to be really dynamic right now, or was in the past, I guess, also.
Any other questions?
Yeah, actually, yeah. So this is Steve. Hi.
Hey, Steve.
Great. Yeah, great talk. That was really fantastic. Really interesting stuff. As somebody who's perpetually interested in dust, strangely enough, I'm wondering about some of the envelope modeling. So you have these amorphous carbons and silicon carbides. Um, so I'm sorry if I missed it. Could you just talk a little bit about the assumptions of the dust grains themselves? I mean, I would assume that they're pretty small in an expanding wind. Is scattering taken into account, or what kind of assumptions were made in the envelope modeling?
Yeah, and so our first approximation was that we treated the envelope because it's still pretty rarefied. We treated it like the sort of outer layers to some degree of IRC 10216 after a certain point. And then we started with, assuming that amorphous carbon would play a larger role in the inner region, and the modeling just wasn't matching. And so when we lowered that effect and increased the amorphous silicon carbon, then our match was there. I have to I have to go back and look if scattering was included. I believe it was, but I guess it's buried in the details of that section. If I and Pablo would be able to speak to it better if he was online, but um,
Oh,
I
no
don't know if I
problem. I can read the paper for sure. I
sure.
just thought if you knew off the top of your head.
Any other questions? I have one, Ed. I did
Sure.
some digging and I looked at this source and it says that there's evidence of a detached shell. So if there was a recent thermal pulse, that makes some sense with all the carbon-13, but is there any archival infrared data that gives a little bit more information about the dust and whether it's been processed at all?
That I don't. We do, and in the paper we're aware of the detached out about 3 arc minutes away. I believe it's a Izuni 1996 is one of the papers that sort of studied it, and yeah. The other thing too, I guess, is of either a thermal pulse or you had an increased period of mass loss rate, is that the density of the amorphous carbon sort of as you're going through the shell, like we had the density falling, and then we had to turn around and then increase the density again at a certain point to then get the model to fit better. So there is definitely that would be part of it too. Is that something maybe a period of higher mass loss rate was within the last few hundreds to thousands of years that made this envelope a little bit more active.
All right, any last questions?
Yeah, I have a question. Do you see any molecular hydrogen lines in this object, either in the XE's data or maybe in the ISO data? This
So
seems like
data, I don't know if we look because I don't know if the resolution would be as good. It hasn't been looked at in XEs at those specific wavelengths that would have it. But right, I mean, our recent result for 10216 was the first detection of H2 towards a asymptotic giant branch star. That would be fun for you 2022 for anyone interested in that. But it isn't one that we figured. There was a follow-up proposal submitted for H2, but YCAN Van wasn't included in that because we didn't expect it to be as strong for its envelope.
I see. Because if you could see it, you'd basically get the temperature of the gas, at least for the H2 is, which might be useful.
Yeah, and that was the basically the idea of now that we showed we can do it, we'd start to, for example, of other stars, let's start tracking down the temperature and the mass loss rate accurately.
All right. Well, thank you so much, Ed. Why don't we thank the speaker? Join us again next week. We're going to continue this series talking about AGN. But yeah, thanks, Ed.
Yeah, again, thanks, Ariel, for asking me to give the talk. Always happy to share XC's results.